Hello everyone. Once again, welcome you all to the course on manufacturing methods. So in this lecture, we are going to discuss about extrusion process. So it's from the same modules, module 2 about metal forming and press work, and this part D will be about extrusion process. Okay. So now what is this extrusion process or how we can define this? So now extrusion process, once again, it's a compression process where basically what happens, the work metal, it is forced to flow through a suitable die opening. So that particular die opening in our case is basically understand die only. Okay, we don't use the word always die opening. So it is forced to flow through a suitable die opening, and thus we produced a desired cross sectional shape. So what basically happens here, you can visualize this extrusion process somewhat similar to an everyday exercise that you routinely do, and which is basically about, like, in the very morning you always like take some toothpaste which is squeezed through the toothpaste cylinder. Okay, and that particular process can be visualized somewhat similar to extrusion process. Okay, so it is somewhat identical to squeezing of toothpaste out of the toothpaste tube. So what you basically do there, so in that particular case, what happens, inside that particular toothpaste tube you have got that particular toothpaste. Okay, which you can visualize as like the metal, okay, work metal, which will flow through that particular die opening, and that particular the opening part, that is the round opening of the toothpaste. Okay, that mouth portion you can consider as if that is the die opening having a specific contour. And in the case of the toothpaste, so what is that particular cross section of the die opening? It is circular, and thus when you squeeze it out, okay, so the work, you can consider the toothpaste as the identical to the work material. Okay, it is forced to flow through the opening, the die opening, and depending on whatever is the cross section of this particular die opening, you get the desired part. Okay, so in our case of the toothpaste, generally just like as it have got the circular cross section, circular opening, which can be considered like the die opening. Okay, so thus we get that particular squeeze out toothpaste as kind of a lump of cylindrical lump, you can consider like that, having cross sectional area as the circle. Okay, so this particular extrusion process, it can also be visualized somewhat similar to closed die forging process. So already we have discussed about all those open die forging, closed die forging, etc. So somewhat it is somewhat similar to closed die forging, because here also later on you'll see we'll have a cylinder. Okay, inside the cylinder that work material will be there, and through the help of a ram or a plunger, basically we apply the force and we squeeze out. In this particular case, it is not squeezing out, we compress that particular material against the die and all, die and the cylinder, and through the die opening, actually what basically happens, the metal falls out. Okay, so in this particular case, so you can very easily see, if you look at this particular figure, so this is the another 3D view you can consider. Okay, so in this particular case, so this hatch area, this is nothing but the cylinder that we have. Okay, and this particular, it's consider, you can consider like the enclosure. Okay, from this particular side it is open, but here we have got this particular ram. Okay, and that ram can give that particular compressive force to the work metal. Okay, so what is the work metal here? So this is the work metal. Okay, and in most of the cases, this is the, it is generally heated, and in most of the cases the shape is like the billet. So we can also consider like the work metal as billet. Okay, so this is the heated billet generally. Okay, and we have got the plunger to or ram to force this particular, compress this particular metal. Okay, and at this particular end, what we have got that particular die of required cross section. Okay, so in this particular case, here in this figure you can see this is the die opening that we have. Okay, and what basically is happening when we are applying force or through this particular plunger or the ram, and we generally have a block, okay, known as the dummy block, which basically is in contact directly in contact with the heated billet and the ram surface. Okay, so we have got this particular dummy block here in between. Okay, this is the dummy block. Now what happens, this force that's whatever force that we apply, okay, so ultimately it is going to compress this particular heated metal here. So as we already know, when it is heated, the metal is heated, so then the strength becomes somewhat less, and the flowability of the metal, etc., already we have discussed. Okay, so what are the characteristics a heated metal has got? So what will happen because of that particular reinforce, actually through this particular die opening, whatever, depending on whatever is the shape, thus the work material will, extruded material will come out. Okay, and this extruded metal becomes our product. Okay, and on what particular phenomenon, or what particular on what basically the shape of this particular extruded metal depends, it basically depends on the shape of the die cavity. Okay, so whatever is the die opening, so not the die cavity, die opening, so that will be the similar to the whatever that extruded metal will come out just like that particular opening only. Okay, so here in by the help of this particular extrusion process, a variety of shapes are possible, and that is basically a variety of shape. It is basically with respect to hot forging hot extrusion only, it is very easy to get different shape, and apart from that, we can also get very fairly close tolerances, and close tolerance, it is an accomplishment of cold extrusion. Okay, so just like the other hot working, cold working we have discussed, so here hot working will mean hot extrusion, cold working will mean cold extrusion process. Okay, and what basically happens, so in a particular process, what is there, so whatever be the setup, that setup remains same. Okay, that means the die, whatever die that we have, the die geometry remains unchanged during the throughout that particular operation. Okay, and because of that, only shapes with a constant cross section over the length, it can be produced. Okay, we cannot like change it like in between. Okay, but if we have to change it, okay, then ultimately the possibility is by changing the die. Okay, the die should have some other different geometry, different opening, then only we can expect that some other geometry as a extruded part you will get. Otherwise the throughout the process, we get parts with constant cross section over the length. Okay, and that is which particular cross section, that is nothing but the die outlet cross section. Whatever is the die outlet cross section or the die opening, that kind of cross section only we are going to get on the particular product. That means if your product, whatever is the look of this particular product, so if you need suppose a star shape product, okay, the over the length, suppose you should have this kind of star like shape. Okay, so in that particular case, the die that you are going to use, okay, the die opening should be like this, like the whatever is the star shape. So in that particular case, what will happen, so the metal, the billet, heated billet will pass through this particular opening portion, star shape, and thus over the length, just like this, you are going to get a star shape. Okay, the constant cross section you are going to get. Similarly, whatever be the cross section that you want, okay, that kind of die you have to make. And in this particular figure, you can see very easily it is kind of 3D view. So like the pressing stem, or it is nothing but the ram. Okay, we have got the container, that is nothing but the cylinder. Okay, and we have all those container liner. So these liners are provided to like some, there are like different possibilities. One is like to maintain the surface. Okay, that means to maintain the surface from wear and tear. Similarly, whatever is the pressing ram that we have, as both of them will be in contact, so smooth like transition of both of them, like proper lining will be there. Okay, and similarly we have this particular billet here. Okay, so to like to hold the bracket die, we can have die bracket, and this is the die opening. Okay, die. Okay, and this is the in between the, you can say, the ram contact surface and the heated metal contact surface. Actually the ram doesn't come, practically it doesn't come directly in contact with the ram surface, heated billet surface. So always that dummy block is inserted in between. And what is the reason of inserting it? Basically, see, if we are thinking using this particular ram, okay, if this particular setup we are using, then a ram of particular diameter or dimension only will require, and along with that, this particular surface, this surface of this ram it's one of the surface. If that particular surface is hampered, then the proper compression of this work material also will not be proper, and like that. Okay, and now as the material generally is heated, the billet is generally heated, so actually to help this particular RAM to retain its proper shape, size, and to so that the heating, whatever is the difficulties associated with all those heated surface, contact with heated surface, etc., those things should not come into picture. So what basically happens in that particular case, in between changing the dummy block, if it is worn out, it's become very easy rather than changing this particular plunger or the RAM. Okay, so what happens if sometimes wear and tear, definitely gradual wear and tear will be there, and during as we are directly in contact with a hot surface, hot metal, so once again some all those oxidation problem, scaling problem, maybe some other problem that may be there, and because of that the surface of the dummy block, it definitely will get worn out. And but as it is a small block, okay, actually what happens, changing the dummy block becomes very easy. Okay, if something happens, you just change it. Okay, and rest things will remain fine. But if we each and every time we have to change the whole plunger itself, then it will be costly. So from economic standpoint of view also, dummy block is good. Now like there are a variety of product, as we have already discussed, which is possible to manufacture with the help of this process. Okay, so different typical products which are made by extrusions, it is like the railings of like sliding doors, window frames are also sometimes made. Okay, tubing of different cross section, ladder frames, numerous structural and architectural shape, etc., can be very easily obtained with the help of this extrusion process. Okay, and there is another possibility. So what is that particular possibility, and which is generally done, is extruded part, it can be cut into desired length. Okay, and then what becomes, the all the single cut part, it becomes the discrete parts. Like examples are like brackets, gears, etc., coat hangers, you can very easily manufacture with the help of this particular extrusion process. Then throughout the cross section length of the length, you will have the same cross section whatever is your required thing, and later on, depending on whatever is the length that you require, based on that length you can cut it. So those things, examples are evident here. So you can see the brackets, okay, maybe gears, coat hangers, etc., are being manufactured by extrusion process. So what will happen initially, as a continuous this kind of part, okay, this kind of extruded part will get the product. Okay, and for this particular, yes, definitely the die opening for this particular part should be like this. Die opening will be in this particular gear will be just like this. Okay, whatever is the shape of this gear. Okay, and through this opening it will come out, and we'll get a product like this. Okay, and after that, depending on whatever should be the length, you can cut it, section it. Okay, so in that particular case, what will happen, a single discrete part like this you can very easily obtain. Okay, so sometimes this kind of questions are being asked, how you can manufacture gears which by the help of this extrusion process. So it's possible after that, but what is the thing, so the as a this kind of product you are going to get from there, required at the required length you have to cut it. Okay, that another process, that another processing step will be there. Okay, and depending on like as we are saying that we have to that molten, that metal, okay, heated metal, it has to flow through the or come out of that particular die opening. So now definitely ductility comes into picture. Okay, so now based on ductility of the metal, it can be carried out at room temperature or elevated temperature. So it's very evident, if the ductility is more, then it is possible to go for cold extrusion, that is at the room temperature also we can do, or in most of the cases we have heated, we billet is generally heated. Okay, and most of the common metal like aluminum, copper, steel, magnesium, etc., generally are extruded. And in this particular figure you can see, as we have already discussed, different shapes. Even the complex shape, it can be very easily extruded. Okay, the cross section of the like if you see this particular heat sink, okay, you can see different various fins are there. Okay, which is acting like this product is acting like a heat sink. Okay, so now this shape, from this particular shape you can very easily see it's a kind of complex shape. Okay, not a very regular shape or very easy kind of shape. So this kind of complex shape also can be very easily produced by the help of this kind of extrusion process. But what is the requirement is the initial die, okay, having the required cross section as the opening. Okay, so that die will, that means will look somewhat like this. Okay, the opening will, depending on whatever is the shape and all. Okay, it's not the figure is very poor, whatever I am drawing. Okay, but whatever is this, you can see whatever is this particular look. Okay, based on that you can have the part. Okay, so it is an example that it's very complex part cross section can be also very easily extruded. Okay, so I hope by this time already you have got the idea and have understood what is extrusion. So now that some question it may come to your mind. So we have also, in case of rolling also we have discussed it. We are producing constant cross section throughout the length. Here also we are doing the same kind of, talking about similar kind of things. So we want to compare and to make a comparison between this extrusion process and rolling process. So what about them? So see, in the case of extrusion also, and if you recall about rolling, so here in the both the cases, constant cross section of the parts, that is the product, over the length that we get. Okay, but in the case of extrusion, what is the good thing about it? Okay, so high complexity of parts is generally possible, but in case of rolling we limit ourselves to generally parts of simpler cross section. Okay, and now as you can see from the process itself, so extrusion, it's a single press process. That means once you apply the compressive force through the ram, okay, and the work material, if it comes out, whenever it comes out through the die opening, actually the process is over, you are getting the required cross section. Okay, but in case of rolling, generally it's a multiplier process. We have seen that the amount of draft that is achievable, etc., okay, it's are limited, and final shape, okay, sometimes it is drastically different from that of the, like we can have the roll pass design to get different forms and all. So all these things already we have discussed, and generally rolling is a multi-pass process. Now in the case of extrusion, the amount of reduction possible is more, but in the case of rolling, it is generally comparatively lesser amount of reduction. As you have already seen, all those different problems were also involved, like rolls of force, roll separating force, etc., etc. So, and the draft achievable draft was and somewhat limited. Okay, and in the with the help of extrusion process, generally we can even go for brittle materials. Okay, it can be very easily extruded. You have to heat it and compress it like that. Okay, and whatever deformation happens, we are not concerned about that, but after that it should come out of this particular die opening. Okay, but in case of rolling, generally like brittle materials are generally not performed. Rolling is not generally performed on brittle material, or it is very difficult. Even if it is performed at elevated temperature, it generally is becomes it's somewhat difficult. Okay, and as can be very easily seen from the previous example, you can see, so getting sharp corners properly is very easy. Okay, you can easily get sharp corners in extrusion process, but getting sharp corners in case of our rolling process is comparatively difficult. So these are some of the comparison between extrusion and rolling. You can see that some of the similarities are also there in case of the constant cross section that is achieved on the parts over its length, but some of the other dissimilarity you have seen. Okay, so now next we are going to discuss about the metal flow, how the metal flows in the extrusion process. Okay, so as you have already seen, we have already discussed that basically the die opening we will have. Okay, and depend, suppose from this side we are applying the force through the help of the ram, okay, or the plunger. Okay, this is the heated billet. Okay, and we have got the die opening here. So now depending on the opening of the die, basically like the metal will come out from this particular die opening. Okay, now in that particular case, okay, actually some deformation on the metal it should happen, it is going to happen, and metal will flow. Okay, metal has to flow, and after that it will come out through this particular uh, like uh, particular zone. Okay, so now particular opening, you can say. Now how basically metal is flowing in case of extrusion. Okay, so the metal flow pattern, it generally influences the quality and the different mechanical properties of the extrusion product, as we have already discussed in all those metal flow, fiber flow, all those things we already know. That means we have got some preferred orientation, and depending on how it is flowing and all, okay, some mechanical properties are also influenced. Okay, so metal flow, it's important. Now In the case of extrusion process, the material generally flows longitudinally, okay, along the length axis it flows, okay, because this is the setup, okay. We have the die opening here. Through the help of the plunger we are doing like this. So this is the axis, longitudinal axis. So along this direction only it is flowing, so it flows longitudinally. Thus the extruded products have an elongated grain structure, so as it is going in this particular direction, and generally the cross sectional area, and in this particular case generally like less, okay. So in that particular case actually it gets elongated, the grains gets elongated, and that is nothing but the preferred orientation of the grain that we get here, okay. And as in this particular case you can see three figures, okay. So like it's we are showing the types of metal flow in extruding with square type. So first figure, it shows the flow patterns which is obtained at low friction or in case of indirect extrusion. About direct extrusion, indirect extrusion we will discuss later on how can we define. So in case of indirect extrusion we get some flow pattern like this. Second figure, it shows the pattern obtained with high friction at the billet chamber interface, okay. So whenever there is somewhat high friction, okay, then how basically its flow pattern is there. And third pattern, it shows the pattern obtained at high friction or in the case of cooling, with cooling of the outer regions of the billet in the chamber, okay. So this is the third case. Now what basically the case of first figure, what you can see, so it's kind of very there is no much figure friction and all, okay. And actually through these grid lines we are dividing the metal, and we are just flowing which portion of the metal is deformed more and all, okay. So with the help of grid line we have just divided the billet with the grid lines, okay. Now you can see like as the metal also works against this particular only opening is only here, so other surfaces are here, okay. Here also gets, the metal gets restricted here, it can only flow through this particular opening. So when we are applying the compressive force here, so once again, like if previously it was this much, so it is grid lines we can consider like it was bigger. So now in the next case, initially if it is like this, okay, suppose, then after compression, okay, what is happening, so it is like this, okay. So that is change, okay. And in this meantime, so the grains, okay, so actually this flowing in this particular zone through the opening, okay. The deformation is generally visible here. Now if you see, look at this particular second and third figure, then you can see there is a particular zone. In this particular first case, it is somewhat like from all the zones is trying to come out of this particular opening, but here you can very distinctly you can see there is certain zone here, similarly here, from where actually the metals are not actually flowing through it, okay. So all the deformation is happening like this, and this portion is coming out, okay. So now in this particular case, in the second figure and figure B and C, the metal at the corners, these corners, it is stationary, it is remaining stationary, okay. And it is this particular situation, it is somewhat similar to, it is actually somewhat similar to like stagnation of fluid flow in channels which has got sharp angles or turns, okay. So as we already know, in the case of flow of fluid, also in case of fluid fluid, okay. So basically here through this particular portion, okay, there will not be any movement at all, okay. So here also this particular this kind of problem is there, okay. So it is so here where there is no movement at all, okay, from where there is no metal flowing, so that is known as the dead zone, okay. So now in this third figure, if you see, so it shows a pattern obtained at high friction or with cooling of the outer regions of the billet in the chamber. So in this particular case, this particular type of pattern, which is generally observed in case of metal, whose strength increases rapidly with decreasing temperature. And because of that, basically what happens, there is a problem associated. So because of that, sometimes a defect which is known as the pipe or extrusion defect, it is formed, okay. So as you can see, like it is vigorously disturbing kind of flow pattern that we are getting, okay. Now this is about it. So we have seen that basically from bigger cross section to smaller cross section, actually here it is generally more, here it is generally less, okay. Now there is a term known as the extrusion ratio, and which is also we have to know while designing all those dies and all, while we are studying about the extrusion process. So now this term extrusion ratio, it's defined as the ratio of cross sectional area of the billet to that of the extruded section. So now this area to this area. Okay, this particular the ratio is known as the cross like extrusion ratio, and generally typical values of extrusion ratio are generally 20 to 50. That kind of reduction we generally say, which is kind of good kind of reduction. Okay, so that is basically about it. So in the next class we'll be discussing about different extrusion classifications and their variables. We'll discuss about direct extrusion, like reverse extrusion, etc., etc. So for this class we will stop here. Thank you.